stand a little closer, so I'm kind of blocking that light. We've kind of hit compressors a lot, and I've learned some new things about compressors recently, like the last 3 weeks. And then I've also been heavily studying journal bearing design, which is pretty crazy. Like, we kind of just like take these things and stick them in there because they fit, and there's a lot of notions on how they work, right? Like we just like, I don't know how to put it, right? Intuitive, right? So there's I've had intuitive ideas about how they function, um, as well as pretty much everybody I've dealt with in automotive type stuff. I never deal with industrial type stuff, so I don't talk to people that get to design these things. So there is way more to them than I originally thought, and it's really cool. I think I'm doing a video on that. It's really neat as to why they're designed how they are. As simple as they look, there is a phenomenal amount of engineering that goes into both the journal and the thrust bearings. I've known about thrust bearings and their shape and tilt. They're not a tilting pad, but they have angled pads, and that stuff for a little bit kind of glanced or glossed over journal bearings, and I've kind of recently come back to them due to needing to understand them better, especially for diagnosing turbos that are coming from other countries to be repaired. You don't want to mess it up and send it back with a very expensive shipping bill as well as parts bill. But today we're going to do introduction to turbine maps. So you thought compressor maps are complicated, just wait until we get into turbine maps. Because instead of pulling from regular atmosphere, the motor becomes the atmosphere on a turbine map. So we need to have quite a few sensors in place to be able to actually look at a turbine map. On top of that, most places don't publish turbine maps. But you don't have to have a map to figure out what's going on. You just need to have the data. You can go look at it because there are general trends. The turbine side is actually mathematically and like physics wise way easier to track what it's doing than the compressor side. The compressor, you're dealing with a positive displacement device with um, something where the compressor's surface speed is higher than the airspeed through it, and it wants to go, it would prefer to go the opposite direction. Um, there's a lot of interesting things going on with compressors versus turbines are pretty straightforward. There's not a lot of real crazy stuff going on. If you can kind of get these kind of base principles, and no, I'm sure I will miss things and not cover things because this can certainly be, there are lectures that go on for hours and hours and hours and days and weeks and months and papers that are several hundred pages, and they're not just one of them, there's a lot of them that go over this. This is going to be a video to help explain the turbine side to the automotive enthusiast without getting really too heavy into equations and in the notion that you can put sensors on this thing, look at it, and probably figure out what's going to be the right move. To get things started, the first thing is that the motor does not care about the turbocharger. I don't know how many times I've got to say that. The motor does not care about the turbocharger. The motor cares about the pressure deltas across itself. So it cares about what the boost pressure is, and it cares about what the drive pressure is. But by understanding what the turbocharger wants, we can then go adjust the turbocharger to hopefully get the pressure deltas at the motor to be more ideal for what we're doing. So the motor could care less what brand it is. It can be, 3D printed and grinded down to a shape and put it on there, and as long as it compresses air and makes drive pressure, or compresses air if it's a blower, supercharger, it's going to do something. It might do something poorly, but it's going to do something. Today's turbo technology and supercharger technology is all pretty great. It's really hard to find gains without really targeting narrow, very narrow operating conditions and engine displacements. Because we have two systems on a turbocharger, we have both the turbine side's state as well as the compressor state. They are two separate entities. Um, they both care about different things. Remember, the compressor is design-wise is easier to account for because it just has kind of a more standard pressure delta, and your inlet conditions are pretty easy to figure out. Unless it's a multi-stage turbo system, your inlet conditions are always your outside conditions, and the amount that your outside conditions can vary is what you're going to use for your test data as far as designing. On your turbine side, your atmosphere is the motor, and the pulse amplitude, so pressure spike per exhaust valve open, RPM of the motor, displacement of the motor, and mainly it's more so displacement per cylinder than it is overall displacement that the turbine side cares about. Really makes a very big difference. We've all seen Hondas that can make way more power on a small turbocharger than a big block with the same turbocharger. All right. With the exact same turbocharger, why is the power output different? It's because the atmosphere for the turbine side is different between these two motors. Your mass flow can actually be the same, but if your amplitudes are higher, which is what happens when displacement per cylinder gets bigger, the condition inside the turbine housing and turbo wheel change. Your temperatures are also going to be different between the two within reason. So, we're going to start. Talked enough. Okay. This terrible handwriting. Should probably just type this out. It looks even worse in reverse. Okay. So your P1 is the exhaust flow. We'll just use this. So this is your drive pressure, and this is your pressure in the downpipe. The only thing that moves the exhaust gas from here through the turbine wheel to here is the pressure delta. If you have 40 pounds of drive pressure and you have 40 pounds of exhaust pressure, your exhaust gas will not move from here to here. This becomes an air compressor, right? You have essentially cut this off, and now as the motor runs, the pressure in here would rise. And now, because pressure rises, now it starts to flow, right? But if you could make sure your exhaust pressure was always the same as drive pressure, you would cut open this channel to atmosphere. And P1 would always match P2, so as the motor continued to run, pressure would continue to go up because the motor is pumping the exhaust gas into a tank, essentially, and it will just continue to go up. So, the only reason your exhaust gas moves through the turbine wheel is because of the pressure delta. And that's it. No magic, no nothing. Now, the rate of flow through the turbine wheel, which is here, right? Your nozzle and turbine wheel are all connected, is the delta between these two pressures. The higher P1 gets without P2 changing, your expansion ratio, ER, gets greater. The higher the expansion ratio, the more volume and mass, because we're dealing with a compressible, will move from P1 to P2 in the same amount of time. It can continue to do this until the speed of the gas through the nozzle reaches Mach 1. It's local speed of sound. When it has reached the local speed of sound, what happens is that the pressure signal that makes its way up to the feed tank, or exhaust manifold, that tells, for lack of a better term, that tells the feed tank that it can continue to move more. What happens is because it's the speed of sound, because that wave that travels up to talk moves at the speed of sound. So once your gas flow speed is at the speed of sound, the signal can no longer make its way up to the tank, and the gas velocity cannot increase. So this is an ideal condition. This does not happen in turbocharging very often. VGTs, surprisingly, something I saw the other day, do this really good. Fixed geometry chargers seem to not do it nearly as well. They run into problems because the housing geometry to turbine wheel geometry versus gas speed, angle of attack, and all that jazz gets out of whack. And the thing gets mad before it even gets there. Which isn't a bad thing. These are the two conditions you can have. Neither one of them is bad or good as long as within the operating parameters of the motor, these are all in check. So, said VGTs do this really well. If you want to check it out, Duramax Tuner Calibrated Performance just did a video where they put a slide valve in the on the engine dyno's downpipe. 1 second. Just a simple slide in the downpipe. Turn that out. So they can raise the exhaust pressure on the dyno. And what's pretty neat is you can, and the power output does not change because the expansion ratio is always way high, meaning with the free-flowing exhaust, the max gas velocity through the turbine wheel was already met way long ago, so it can't get any higher. And then as you close down the slide valve and raise the exhaust pressure, the vanes compensate to raise the drive pressure to maintain enough expansion ratio energy to hit the same boost target. And because that target just so happens to be still pretty much at the Mach limit of most turbine wheels, there's no change in the power. Right, that's pretty cool. Given the motor has to be designed to operate at the higher drive pressure conditions, this motor is designed to operate with the VGT turbocharger. So cam head, all that stuff, right? It's all designed around the fact that you're going to have high drive pressure, and as long as the design of the motor is made for that, then you're in good shape. Most of your factory diesel motors are all designed for high drive pressures. And the other side of this is when people turbocharge normally aspirated designed motors, right? So like your NA motors that are designed to be NA really do care about the drive to boost ratio at a very low drive to boost ratio, wherein motors designed to already be factory turbocharged that have the higher drive to boost ratio right out of the gate, the engineers account for that, and you don't see nearly the gains on systems where the head and cam's designed for that versus if you take an NA motor at 2-to-1 and you drop it to 1-to-1, there's a big gain there. Usually, I mean, we're not trying to, I'm sure there's some NA motor that's so terrible that it doesn't matter what happens. So I think we got like pretty good understand, right? So P1 can continue to go up. Above P2, the flow will continue to increase until the velocity is at the speed of sound. This is local speed of sound, not our local speed of sound just standing outside. You have to factor in temperature and pressure to find the new speed of sound, and you can see what that is. Looking at data on gas engines, at least with the 6067, it seems to get really, it's getting like really unhappy at around a 2.0, or not a 2.0, I should say. It's getting really unhappy at about 65% the speed of sound. And that's because the compressor size is allowing the turbine to get up to a turbine speed that makes the angle of attack very poor. So the ability to actually move the gas into the turbine wheel volute has become inefficient instead of the velocity of the gas being inefficient. So there's like two examples of where the turbine is having a problem. because the compressor can't hold on to it. And then there's the other one where, like I said, VGTs do it really good. And they give you all the data, which is awesome, on that calibrated power bit. You can go look at it. It's like a 4:4 expansion ratio. With the 5-inch exhaust, it's 320 something, I think, with 12 psi, and it's 289, 2.89, I think, with 15 psi. They're simulating emissions equipment being on. And you can watch the vane position increase to raise the pressure in the manifold or in the turbine housing to maintain the same exhaust mass flow energy, because you need those pressure deltas to the turbine wheel, so the turbine wheel could continue to produce the energy required to meet the boost target that the system was asking for. Does it all kind of make sense? I think it does. It makes sense to me. Then changing the turbine wheel shape or the housing shape and all that stuff, it changes where the engine RPM is in relation to when these points meet one another, I guess. Right? We should probably save that for another video. We're already at 17 minutes. It's going to get ridiculously long. Let's look at compound turbos. Compound turbo exhaust sides, we have turbine housing 1, drive pressure, which feeds to interstage drive. Interstage drive then feeds to atmosphere. So what happens with these, remember the only reason these things move from here to here is the pressure deltas. What happens with the small, if the atmospheric charger's exhaust side's too small, your drive, your interstage drive, can go up, and your drive here can go up, not as high, right? So then go straight up there, and we go over here. What that does is it reduces your gas exchange rate from P1 to P2. And what that does is it takes energy away from your manifold turbine side. You lose energy to drive the compressor. And in compounds, you need all the energy you can get, because P2's compressor is increasing all kinds of density. It's increasing the density of the working fluid on P1, as well as it's lowering the pressure ratio on P1. So we have a lot of things trying to slow P1 down. And what will happen is you can take P1's turbine side, and if you slow it down to the point where the turbine's inefficient, then the pressure stacks up. Right? The pressure will stack up here. You'll be stuck with the same exchange rate through here, and then to the atmosphere. That kind of makes sense. This is what I've been doing for like the last 2 years. Yeah. Once this clicked, this is how I've been sizing things. And it works amazing. And it doesn't mean you get it right the first time. Usually to kind of figure this stuff out, you have to do you just have to throw something at the wall at some point, and then put sensors on it so you can gather the data. And then once you can look at the data, now you can make a change. And then the next time you go and throw the stuff at the wall, you have data behind you to do this. But this is a big deal. So on a lot of setups, what I've been doing is taking P2's interstage drive pressure and putting a bigger turbine housing on it or a bigger turbine wheel in it. What's that do? It'll lower interstage drive, because the bigger the turbine housing or the bigger the turbine wheel, the more mass and volume you can move through per moment of time. The mass of the working fluid moved through the turbine wheel per unit time is part of the turbine work equation. That's how you can get to larger and larger turbine housings and larger turbine wheels. And the drive pressure will go down and the boost pressure can go up. Or, yes, that's correct, is because we're trading off pressure energy for mass energy. Now, it does also make the Atmo less responsive, right? There's all the caveats, catch-22s to that. But in this case, we try to size the P1 stage to work correctly and to take care of that. And then we can run the atmospheric stage in a state where when we hit the target pressure that we're looking to run in the inner stage, our interstage drive pressure is as low as it realistically can be. What that does is it allows P1 to still move as close to the same amount of exhaust gas as it could as a single into the inner stage, and then the inner stage transfer rate out to atmosphere is kind of what it's going to be. It's just like this one's running just like it was a single charger, just gets less energy. This one's running like it's a manifold charger with way more atmosphere than any compressor map could ever show you that you had. So, velocity is a big factor of your gas velocity. Is your pressure deltas. Your density is a factor of compression and temperature. So you get compression as your drive pressure goes up, your exhaust gas becomes more compressed. As the temperature goes up, the exhaust gas increases in pressure but reduces in its weight per cubic foot. The temperature sets up your speed of sound limitations, as well as the pressure. Sets up your speed limit, right? And ideally, you can't go any faster than that. Then volume is mainly a geometric constraint as far as the angle of attack of the exhaust gas into the turbine wheel. It's like a turbine blade, right? And there's one last thing. Guess we can maybe just do a short little bit on sizing, but we probably should do that in a different video. As far as sizing, like your chargers, what's so far in, like I said, recent time, what's been working the absolute best is taking this into consideration when choosing the sizes. So the more restrictive the manifold charger is, the smaller the Atmos turbine side can be. So we're not taking into consideration speed and all that. Oh, I was going to add, I know what I was going to do. Let me finish this and we'll do that. So the more restrictive the manifold charger is on your P1 to P2, the smaller the atmospheric charger can be. The more your manifold charger flows, the less restrictive your atmospheric needs to be. Because what will happen is if your manifold charger's exhaust side flows too much, what will happen is your P1 and P2 pressures will get too close together. All the load will sit on the P2's turbine side. And what will happen is no matter where you adjust the gate on this thing, it will have the same drive pressure and want to make the same boost pressure. And there's a lot of other domino effect stuff that happens that's no fun. But that's how I've been sizing compounds now for a little bit, and it's working awesome. It's either working good, meaning that it's close to ideal and sometimes they need revisions, or it's pretty dang close to what we're after. As far as screw-ups go, I know about this because I've screwed it up quite a few times, where I make P1 flow too much without making sure P2 flows enough, your Atmo, on the turbine side, and the system's terrible. Like, it runs like garbage every single time. And it was really confusing at first until this made sense. And it seems really simple now to like think about, but at the time it didn't. But this is, you can watch this happen, which makes it cool. At the very end of this, then I'm going to put on, or we'll do it for the next video. We will plot out some points on a turbine map. If you go look at turbine maps, you'll notice that almost all turbine maps max out at a 3.0 pressure ratio. Or expansion ratio, pressure ratio, it's the same thing for these things. That is because the gas velocity can't go any faster. Because you're transferring something to atmosphere. So on a compressor, you were positively putting somewhere where it can't go anywhere else. So the pressure ratio can be really high. On the exhaust side, we are only moving exhaust gas through pressure deltas. So the rate at which it can move from stage manifold to atmosphere is governed by the speed of sound through the nozzle. So because we can't go faster than the speed of sound through the nozzle, it just so happens that the speed of sound through the nozzle generally occurs at around the 3.0 expansion ratio. There are cases where it's higher with really, 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 really big turbochargers because the area finally gets large enough. And if you look at smaller turbochargers, they tend to incur this issue at lower expansion ratios, and that's because of the curtain area of the nozzle and the area through the turbine wheel is smaller, so their rate of climb and your P1, P2 overall speed grows a lot faster in with the same mass flow. So hope this is helpful. On the next one, we can do some turbine maps, and not just like the Garrett turbine maps, but like actual scientific turbine maps, and take a look at how this stuff works. So I hope you hopefully enjoyed this one. This is definitely, it's really complicated at first because there's not a lot about it in the automotive industry, performance-wise. We don't see it. We get preached compressor map, compressor map, compressor map, compressor map, compressor map. The compressor map has nothing to do with the turbine map. Well, unless we're going to factor in the rotor speed, but let's just say you can have a compressor that's running at 80% compressor efficiency, and you can have a turbine that's royally unhappy at 40% efficiency. That is definitely something you can have. So it's not talked about. There's not a lot of them published, and that's kind of where the magic comes from with sizing turbochargers to applications, is actually more so on sizing the turbine side and housing to be proper for motor displacement, rev range, versus trying to size the compressor to be right. Compressors are pretty easy to size right. They all run pretty good. Making sure the turbine's good is a whole different world. Remember, your atmosphere is your engine. You guys, you have a good one. You enjoyed this? Thank you.